So welcome back, everyone, and please welcome Roman. And I have to say, it took us 5 MICES conferences till someone brings cats to MICES. So that's a great idea. And but even more, I think we're looking forward to Roman's talk about reinforcement learning in search.
Okay, so uh, welcome everyone. My name is Grebennikov Roman, and today we're going to talk about reinforcement learning in search. And just a short intro about myself. I'm doing machine learning for quite some time in different areas, and for the last, I guess, 5 years, I'm working as a relevancy and ranking engineer at Findify. And Findify itself is a company, is a white labeled e-commerce search, which as it's white labeled, you never notice that the brand store is using Findify because it's tightly integrated, but we're not large, not small, not Amazon definitely, and not Google, but we do have some traffic, so we have some place to do some weird machine learning related experiments. And the talk itself is mostly about the thing called personalization, but not like the personalization in the old days when you personalize the experience of the e-commerce store for the returning visitors, but like the things happening inside of the session, because Findify is mostly focused on small and medium e-commerce businesses. And for these businesses, there's not so many returning customers at all. Like on average, it's only 20% of customers returning in half a year. So it's not that much as for Zalando, for example, or for Amazon. And this talk is also not check out how we did a good thing. It's mostly about how we failed miserably multiple times trying to implement different smart ideas on the ranking, and our current mental model about how it should work. Probably the next year there will be talk about why it was also wrong, but who knows, we'll see. And we'll just overview different methods and solutions of the reinforcement learning and why it is important, and with all the pros and cons and what we found while trying to implement it in production. So as this conference is focused on search, it's like e-commerce search, this talk is also about ranking in search, but the ideas of the reinforcement learning are applicable also to other areas, like for listings, for recommendations, for whatever you want. But still, we're going to talk about search. And if you take Elasticsearch from like out of the box and try to send some queries, the results will be ranked by the algorithm called BM25 or TF-IDF if the Elasticsearch is old, but still BM25 is just like a matching function which tries to compare, like to match your query into the document, but itself it's still based only on the text of the query and the text of the document, on the frequency of words, of the number of words. But as we're on e-commerce, we also know that there is much more diverse metadata available about the query, about the customer, about the product, which we can also plug into our final ranking. But default Elasticsearch ranking is not allowing us to do it easily until we do some weird things with it. And the problem with a just pure text-based matching is that there are some queries which are non-navigational. They're like a discovery queries. When I'm looking for jeans on a store, I have no idea what particular jeans I'm looking for, and I don't know what should I click on out of 16,000 results found. So, and for me as a customer of the stores which are running on even on our platforms, we know that my focus as a customer is quite narrow. If there is no relevant product on top of like top 5, top 10 products, I will probably leave. This behavior is more specific even on mobile because the screen is smaller, there is less products you can fit on the screen. So people are just leaving and bouncing and not coming back. They might come back to Amazon or to Google because there is no other Amazon or Google, but for small to medium stores, there is plenty of alternatives. So the first items is really important. It's important what you put there. And for us as a like e-commerce platform, it's hard to, it's easy to lose a customer of our customers. So why don't we just plug all this metadata directly into the ranking? Just take the number of clicks, mix it with the relevancy score, and call it a day and see what will happen. So if we have a relevancy, or if we have a couple of products returned in our search results with similar text relevancy score, but different popularity, we just rank more popular products higher. It works, actually, surprisingly. But any data scientist will tell you that you should not stop on that. You should add some constants there. You should tune your model so it will provide better results at the end. And the problem with this approach is that it's really hard to stop yourself from adding things into this ranking formula. Why don't we add page use, purchases, cards, just windows for different time dates, more constants to tune at the end. And then we'll get some sort of a ranking formula, which is too complicated for a human to understand what's going on, and probably won't work out of the box because it requires training. Because the complexity of such approaches to rank, like heuristical approaches to ranking, has some sort of a limit of human understanding what's going on. So, and then if it needs some sort of a training, then you're coming into the path of learning to rank. And learning to rank is that approach to ranking when you are not directly defining how your system should rank. You just show some sort of a training data to the system and ask it to generate some algorithm for you, how it should be ranked, to maximize some sort of goal you set. For learn to rank in search, there are two major approaches for generating this training data. The first one is with explicit query grades. So we have experts which are grading the quality of search results for specific queries, and it's not really working for Findify because there are just too many stores, too many queries. You cannot just find experts for everyone. And there is another option that you use customer behavior, like customer clicks, purchases, and other interactions as a source of training data for your machine learning problems. So for example, you have like the same 3 products, and you know that the second product was clicked. So you assume that product 2 maybe was relevant, product 1 maybe was not relevant because it was probably evaluated but not clicked, and that's not clear what to do with product 3 because it was probably not evaluated at all. But using clicks as a source of truth, as a source of training data for learn to rank problems has some own issues we encountered a couple of times. The first thing is that not all the products are created equals. This diagram is like a histogram of clicks for different products, and you see that there is like a lot of winners with products which receive a lot of clicks, and there is a lot of losers. And if you try to increase amount of clicks, you might increase the wrong place, because the more clickable products might become even more clickable, and they can cannibalize the clickability of this not really clickable products. And from the margin perspective, it can be like a disaster, because these products might not have high margins, so your business metrics might suffer. But it's not the only thing which can happen to you. The second part of the problems is like a model bias. Imagine that you have your machine learning model, which ranks your products, deployed into production. It emits some sort of a ranking, which is shown to customers which click on these products. And then this click stream is fed back into the model as a training data. So the model takes its own rankings and clicks on these rankings as an input for the training in a loop. And it might generate the same issue as here, but not with the popular products, but with the products model for some reason likes. So it decides that, okay, this product is relevant for this query, maybe it's not popular, but still relevant for this query, and it will start promoting it and promoting higher and higher. It will receive more clicks and will be just promoted higher and higher again and again, and you will get some sort of a like self-degrading search. And the last, so we observed it a couple of times when we enabled personalization for stores which had no personalization before. So like on a business metrics, it sees like a bump, like increase, for example, in conversion, and then slowly degradation, because here the data on the left before like enabling was not biased and not affected by the model itself, and on the right is biased and affected by the model. And the more it fills the training data set, the worse the results. And the last and not least is the position bias. People are clicking on the first elements of the search just because they are first. So we just got spoiled by Google that first 3 results are relevant and other don't exist. This is also present in e-commerce, not only on Google. And we once did an experiment. So we just shuffled search results for a small segment of customers and tried to compare the positions of clicks compared to the normal ranking. And looks like that there's not that much difference for the positions of the clicks. Yes, there is a small drop on the first position, and in general, there is less clicks on this type of ranking, but positions are still the same. So business metrics are going down as there are less clicks, but positions are there because people got used on clicking on top. So with all these biases, it's unclear what we can do, but there is an interesting idea that, okay, if we have bias and this bias itself is like, maybe this bias can be separated out of the true relevancy of our products and so we have some sort of observed relevancy. Okay, this customer made a click here, but we know that it contains of 2 parts, like the true relevancy, like the intent of the customer while doing this click, and the bias. So like the impact of position, the impact of popularity, the impact of the model putting this element somewhere here. So might be we can estimate this bias and then just remove this bias and then call it a day, because we will get our true relevancy. There is a paper from Google called like position bias estimation, but it highlights an interesting approach called inverse propensity weighting. That, okay, the offline training data is biased, but there are ways you can do to remove this, to estimate this bias and then to remove. So at first, you downsample the navigational queries because for these queries, people are always clicking on the first results because they're searching for a specific product and they are not doing any discoveries at all. And the second part, the most important part, is like a document level propensity. So we're trying to estimate what is the independent probability of the click on a specific position, independent of the relevancy itself. So how it works. So you have a query for socks and you shuffle search results for this query, and you know that, okay, the socks with a Star Wars on position 1 was clicked 50 times, when on another option of shuffling it was shown on position 5, it got 20 clicks, and on position 25 it got only 3 clicks. So it's the same context, the same query, the same product, but shown on different positions, it gets different amount of clicks. So at the end, you can aggregate this information, this distribution over different products for the same context, for the same query, or across the whole store, for example. And you can get some estimation of this impact of the position on the probability of the click. So it's technically just a position bias. And you can just subtract it and call it a day and put the true relevancy value into your reinforcement learning model. There are some pros and cons to this approach. Like still estimation depends on context and on search query. And there's usually a lot of context and a lot of search queries, and you need to have quite a lot of traffic to do this estimation. If you do the estimation wrongly, you just had not enough data for this estimation, you might introduce yet another bias. And you still need to do some sort of shuffling of the search results, which might influence your business metrics at the end. So like if I was Google, probably it would be fine, but I'm not Google, and probably most of the attendees of this talk are not Google. So we need to think about some alternatives to that. So as we know that production training data is biased and there is nothing we can do, and biasing is hard, maybe we just can't go online and to use another approach for the training and do a reinforcement learning. So reinforcement learning approach in machine learning is just consists of two stages. On the first stage, you explore, you poke real people, you play with different types of ranking right in the production and see how people react into these rankings and to this algorithm. And then you extract some sort of knowledge about how do people react, and then use it for better search results. So for example, and at the final goal, what you're trying to exploit is to, like, from reinforcement learning terminologies, minimizing regret or maximizing the reward. And for example, your business metrics, like the true business metrics, not the NDCG, but for example, the conversion. And all this reinforcement learning magic based on the idea of multi-arm bandits. Multi-arm bandits is just a row of slot machines in casino, and you're trying to play on the slot machine. Your goal is to make the maximum amount of money, and slot machines has different winning probability, but you just don't know this probability. And what you can do, you can explore. You just throw random coins into all of the slot machines and write down the probability of the winning, like the estimation of the probability of the winning of each slot machine. And then you use some sort of a strategy how to exploit this knowledge. So there is a greedy strategy. So you compute the average winning success rate for each slot machine and play on that one. But what if you was not right on your estimation? There is an epsilon greedy approach, is that you sometimes still throw coins onto some other slot machines just to make sure that your estimation is correct. And like state of the art in this area is lean UCB approach, is linear upper confidence bound. As your estimations are still probabilistic, so there is a confidence bounds there, like an upper and down. So you know that with a confidence bound of 95%, the winning probability is within 80 to 95%. So you choose the machine with the highest upper confidence bound and play for it. What happens? So you have like 3 slot machines. This one looks like the highest average winning rate, but not the highest upper confidence bound, because you're quite sure about its winning rate. And what happens here, like you are choosing the arm with the highest optimistic reward. When you won, okay, you got your reward, you got a click. And if you lost, the upper confidence bound goes down. Your estimation shifts because it was not the proper estimation, and your algorithm on the next iteration might switch to another arm. But what is arm if we're talking about search? Because on search it's not clear what is an arm. So it can be a document. It might work if your inventory size is not huge. For example, you rank news articles. There are not so many news articles to rank, so you can use document as an arm. But usually in e-commerce, the inventory size is quite large, a couple of thousands of items, and you can think about it from the different perspective. You can use a feature as an arm, like a machine learning feature, like a price of the product, or its popularity, or is the customers from mobile or from desktop. It still can be an arm from the multi-arm bandit perspective. And the simplest bridge between the lean UCB and click models with the search is a model called Cascade Lean UCB. It looks a bit scary, but don't worry. It's just a lean. So your score, like you use to rank your products, consists of just a linear combination of features weighted by something. So for example, this one is the text relevancy BM25 score, and this one is product popularity or product price, and this one is weight. And on each iteration, you choose a random arm, you choose a random feature, and try to increase or decrease this weight of this feature in the ranking function, up or down. And observe how it compares to your reference, like to your previous iteration on the not altered version of the ranking. And you just observe the reward, it's like a dynamic A/B test happening in real time when all the A/B test segments are generated by the algorithm. And if your reward goes up, then you assume that this mutation of the function, of the ranking function, was successful, and you define it as a new reference version and go to yet another iteration of modifications of the ranking function. It seems to be a nice thing, but there are pros and cons as usual. So in practice, we try to play with this approach. And the cool thing is that the reward function here is not directly tied to the ranking function. So there is a score you use to rank, and there is a reward, for example, CTR or conversion. And they're not really tied together. So it can be anything like weather. So you can even combine multiple business objectives here, like CTR and conversion, because it's not really important if it's measurable on general on A/B test, it can be plugged directly to Cascadely in UCB. It's still easy to explain because it's just a linear model with weights, but it requires quite a lot of time to converge because it's not each interaction with your model is not directly changing the weights. You need to observe quite a lot of data to have some confident decision, to make some confident decision if this mutation is considered okay or not. And it's still linear model, and if you have some non-linearities or something like related features, you might have problems tuning it. There is another option of playing with reinforcement learning and the search when your reward becomes the NDCG itself. So yes, you cannot plug any like conversion or CTR before to optimize it, but the cool thing is that you can optimize much faster. So don't be scared about the math here, but it's still just on each click, we just update weights to minimize our loss, or to maximize the reward, or to minimize the regret. So the approach of this PDGD is, so the PDGD algorithm is actually the same as CPR. So it's still linear combination, but instead of observing some business metric, we plug NDCG directly into the weight update algorithm. It looks scary, but it's not that scary. It's just a gradient. And then you can achieve some better things. So it's much faster to converge. Each click matters, and it can be converged much faster. But there is no way to plug some custom rewards. You're locked into NDCG, or you need to derive these gradients for conversion or some other measure. It's still easy to explain. It has the same issues with linearity as the previous model, but what if we want to do something more complex? So if we want to plug more features, or want to plug more nonlinear features on features which are correlated together, and we don't really care about explainability. There is a paper from Amazon about a thing called collaborative pairwise ranking, which is from the last September or something, so it's quite fresh. And the idea is that, okay, let's take the approach of plugging a gradient as a reward for our algorithm, but use not a regression as a baseline algorithm for all this ranking, but the model frequently used in recommendations, like matrix factorization algorithm. If you ever build a recommendation algorithm, you saw these approaches. So sorry for my drawings, but the idea is here that, okay, you have a large matrix of interactions between users and items. If there was a click from user A to item 1, you just put 1 here. If there was no click, there is just nothing. The matrix is sparse with holes. But then you do some sort of a magic. You decompose this matrix according to this ALS or SVD algorithm into 2 smaller matrices on the sides. And then when these matrices are multiplied back together in these holes, you get this predictions of the a relevancy of this item to the user, even if this user never interacted with this item. It's just a prediction. In CPR model, they went a bit deeper and also split this user-specific metrics and item-specific metrics in two parts for hidden latent features and some explicit ones dependent on the, for example, product price or some other metadata related to the product popularity, and some other metadata related to the customer, for example, mobile user or desktop user. But it's still, while doing this composition and decomposition, it tries to minimize this pairwise loss. It's literally just minimize the NDCG at the end, and does it in a non-really linear way. So you can go with you can achieve better results for the quality, but still there are some pros and cons. The main con is math, because it's not linear regression anymore, and if it's easy to fail there, and it's hard to update this metrics in real time, but there are some tricks, and it still focuses on pairwise loss, and or focuses on NDCG, and in ranking, focusing on NDCG is not always the best idea. I will tell you a bit later why. And it's not explainable. So that's actually the current state of the art of reinforcement learning for search. And the main outcome is that there is no silver bullet through this algorithm. So most of the advanced algorithms are focusing on NDCG, and NDCG is not really a business metric. So we observed cases when NDCG went up after some sort of search algorithm modification, but business metrics went down. So it's literally when customer made a click, they made it higher. So NDCG went up, but on average, there were just less clicks and more bounces than CTR and conversion went down. So it's hard to focus on a true business metrics. So my advice is just maybe understand what you're trying to increase and what's the final goal of the company. And maybe if you have different models with different pros and cons, you can combine them together to combine their strengths, or instead combine their weaknesses. It depends. So that's all for today. The slides are already on the internet. It's me if you want to chat. It's a QR code with surprise if you want. And that's all. We have maybe 4 minutes for questions.
Thank you very much, Roman. So maybe I can go first this time. So my impression with reinforcement learning has always been that for many sites, it could be a problem to get the traffic to really do reinforcement learning. Are you saying by defining the arms better, and you can solve this? And you described that your clients might not have that much traffic, so you seem to solve it that way, is it?
Yeah, you're right, but it still depends on the amount of arms you have. So if you are not trying to build an algorithm dependent on 500 different features, and you just use only a bunch of 3, 5, but the core ones, that can be worth it. Because if it's possible to have some sort of an A/B test on this customer, then it can be automated. So you can treat reinforcement learning as a way to automate a continuous flow of automated A/B tests. So it's just playing with different approaches to ranking and marking the ones which are work, and then just playing with them a bit more. So if it's possible to run A/B tests, it's possible to have some sort of reinforcement learning. That's
encouraging. Okay. I see 2 questions somehow related from Daniel and Gennady. So Daniel says, amazing talk. I'm curious, does this approach generalize to sessions that might include more than one query? And also, I'm thinking of the distinction between queries with low demand entropy and versus queries with high demand entropy. So search by product name maybe versus search for high level category queries. And Gennady actually asks about how can you train a model for rare long tail queries? So basically somehow related to the two. Yeah, so how does it relate to the types of queries?
So I guess that's hard to improve anything on navigational queries. So if you're looking for a cat food for your cat, you're not going to try new food every week. So probably you know exactly the brand, the type, the size. So and you probably will just click on the first element because it's just some sort of navigational queries. But if those queries are not navigational, like discovery queries, that can be worth it. So you need to clearly distinguish when it works and when it's not. So for long tail queries, it's more about query understanding and finding the exact product you're looking for. And usually there is nothing you can do with learn to rank there, because if you have a perfect search system, there will be just a single product, because it is one, it's looking for it, and the customer is looking for it. But for discovery queries like jeans, I don't know what jeans I like.
Okay. And the other part of Daniel's question was, does this approach generalize to sessions that might include more than one query? So I think this is more hypothetical.
I think yes, because it's more about the way you do feature engineering. So for example, you can add a feature which is dependent on the previous query. Okay, like the difference between the amount of products from the previous query and for this query, for this particular customer. So if it's like a more detailed query, or like difference in number of terms between this query and the previously done by this customer, it's just up to you how you define the features. For the reinforcement learning, it doesn't really care, just some numbers. It does its crunching.
Okay, I think final question from I picked Julia's question. Can you speak about the kind of infrastructure you need to have in place to achieve OLTR? So,
I think it's the same as for just regular LTR. So you need to have all this advanced machine learning models require you to have some data infrastructure. So you need to have like a clear way to receive updates, like the telemetry from your customers, like how do they interact with your website in real time. And you need to also have some historical data of this interaction. So if you have these things, it's like up to you.
all right. So I think we are already over time. Thank you very much again, Roman. And I hope you're around in the spatial chat, and you can also reply to questions on the Slack on the Zoom channel here. So.